Okay, today, on another edition of Mathing with Grant, we're gonna talk about roots. Oh, that's a bad R. So the first thing we're gonna do when we talk about roots and zeros is the fundamental theorem of algebra. So I'm just gonna shorten that to the FTA. And that is every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers, which means if we have x cubed plus 25x, which, wow, that's not a polynomial, so we're going to do x in parentheses x squared plus 25. We have to get that 25 by itself at the end. So this should have this number of roots. So it has 2. Right? So let's think of another one. If we have x to the 5th plus 18, I'm just making these up, it should have 5 roots. Okay, let me draw a little thumbs up. There. Oh, that's not what I was trying to do. So now we're going to talk about the corollary to the fundamental theorem of algebra. So C to the FTA. A polynomial equation of degree n has exactly n roots in the set of complex numbers, including repeated roots. So it's kind of like this. This is the example I'm going to give you. So 3 squared, that's not squared, that's cubed. X cubed minus x squared plus 4 still has this number of roots. So it has 3 roots. TS. 3 roots. Looks like routes. So now this is where it gets just great. Descartes' rule of signs. The number of positive real zeros of p of x is the same as the number of changes in sign of the coefficients of the terms, or is less than this by an even number. And the second rule, and the number of negative real zeros is p of x is the same as the number of changes in sign of the coefficients of the terms of p of x, negative x, or is less than this by an even number. So that probably, for me, watching this, I'm terrible at audio, and I probably would have forgotten that already. So we're going to go to state. Okay, we're going to do an example of this Descartes' rule. So ES, big exclamation mark, because we're excited to learn Descartes' rule of signs. So, this is a gigantic problem, and by problem I mean polynomial. So f of x, I'm going to try to write it all neat and stuff. F of x equals, and then I'll have this written already right now. So, this is our big polynomial. So what it says is that all the sign changes, we're going to count all the sign changes right now. So this is a polynomial. Okay, so from x to the 6th to 3x to the 5th, there's no sign change. Well, there wouldn't be. This is impossible. And then to the next one, you get 3x to the 5th minus 4x to the 4th, so this is plus, this is minus, so there's one sign change. No sign change here, one sign change here, one here, and one here. So we have 4 sign changes. So now we're going to rewrite it as a f to negative x. So f of negative x equals, I'll have it right after this jump cut. Okay, so here's our second one. I'm going to separate this by a big line. So we now have, we flipped the signs of these. We didn't flip the sign of this. No coefficient. So now we're going to have a big chart over here. 3 columns. And this is the fun part. So we're going to list. So there were, okay, so positive, negative, imaginary. Okay. So positive, we have 4 sign changes. So 4. So 4, 2, 2, 0, 0. And then in negative we have, oh, I forgot to write the sign changes for here. So it goes from positive 6 to negative 3. So this is actually, you can have one here. So 1 sign change here, and then 1 in between negative 4x to the 4th, between that and positive 6x to the 3rd. So there's 2 sign changes here. So we have 2, 0, 2, 0, 2, 0. And then the imaginary column will be how many it will take to get to 6, which is these sign changes added together. So it will take 0 for 4 plus 2, that is 6. And then 4 plus 0, that'll take 2. 2 plus 2 is 4, that'll take 2. 2 and 0, that'll take 4. This will also take 4. And then this will take 6. So that is that theorem. This is the little table that we came up with. It looks much better on the screen than it does on my paper. So that's the confusing Descartes rule. It's not that confusing, it's just Descartes' rule of signs. So, on to the next one. Complex conjugates theorem. So A and B are real numbers and B can't equal 0. So if A plus BI, here I'm going to write this. If A plus BI, I the imaginary number, is a 0 of a polynomial function with real coefficients, then A minus BI is also a 0 of the function. So you basically just say that negative BI is going to be one of the zeros, or A minus 1 BI is going to be one of the zeros of the polynomial if A plus BI is. So if 3 plus 4 I is a 0 of the function f of x equals x to the 3rd minus 4x to the 2nd plus 13x plus 50, what is the other complex 0 of the function? You don't really need to remember that polynomial, because you know from up here that we're just going to flip this sign, and 3 minus 4i is also a 0. So these are both zeros. So if you guys want to math like I do, then you can now, because I just taught you a little secret about mathing. Roots and zeros, wow. So thank you for watching my video tutorial on roots and zeros. have a nice day, I hope.